All right. Last session, I think. How you guys doing? Good? All right, so welcome to our session, Interweaving Compute and Memory for Improved Performance with LLMs. I'm George Williams, Head of AI at GSI Technology, and...
I'm Euicheol from SK Hynix. Nice to meet you.
This is the first time we've met each other. We were asked to put two presentations into one. We have a lot of content, so let's get started. Quickly, we're going to motivate the need for a process in memory or compute in memory for large language models. I think the whole day of presentations has been motivating this. I'll talk about my company's In-SRAM technology for doing this. And then we'll get into SK Hynix's great solution that's based off of DRAM. All right, so I think it's an understatement to say that OpenAI's ChatGPT is revolutionizing chatbots and possibly even online search soon. Gartner predicts that 80% of enterprises will be using large language models by 2026. It's not too far away. Hyperscalers such as Microsoft and Google have been playing a little catch-up here, deploying power-hungry GPU farms and even designing their own chips to meet the demand. Already, data centers are seeing increased operational expense just from Gen AI workloads. And these large language models are big, computationally expensive, and require a lot of power. So in this talk, we will propose unique accelerator solutions combining compute and memory, which provide better energy efficiency.
Okay, actually, we have two questions here. First one is that is GPU sufficient for LLM inference generation now? So let's quickly calculate the GPU performance for LLM inference service. So in case of 175 billion model size LLM, then assuming just a 16-bit precision, it needs 350 gigabytes of memory capacity. So that capacity, then 5 GPU-A, this GPU-A means that H100 card. So 5 GPU-A cards can provide 15 terabytes per second of memory bandwidth. So the processing time per one token is 23 milliseconds, and whole inference latency for 300 tokens will be around 7 seconds. So it's very simple math, just dividing. So compared to existing services, this is very slow, you know. So why is it so slow with expensive GPU? So as you can see on the line graph on the right, so GPU-A can provide 990 teraflops of performance. So in case of training, then you can fully utilize the GPU performance as shown on the graph. However, in the case of LLM inference with just a single batch, then only 3 teraflops of performance can be utilized. So you are paying high price of GPU, but only using 0.3% of performance and wasting GPU power consumptions. Therefore, there is a need to create higher performing and more energy efficient computing infra for LLM service than GPU. Then second question is, then why PIM as a LLM inference accelerator? So left figure shows that the proportion of a memory-intensive processing time increases as the AI model size increases. So you can see that in the bottom model, the proportion of a memory-intensive function is only about 5%. But changing to or LLM such as GPT-2, so it increases to 45%. And as the model size continues to increase, in case of the 175 billion model, it goes up to 92%. So the overall performance depends on the memory bandwidth. Actually, the memory intensive function we are talking about here is just only GEMV function, which is matrix and vector multiplication. And right picture shows that the concept of the PIM. PIM can utilize that higher bandwidth inside the memory by operating processing unit on each memory banks in parallel. And in addition, since only the result data is transmitted, so the data transmission between XPU and memory is reduced, so improving energy efficiency as well. So that's why we believe that this kind of memory and computing units interweaving is the best option for LLM inference, which is very memory intensive task. So now it's up to you.
Great, thank you. So I'll talk a little bit about my company's solution, which leverages SRAM. All right. So now both GPUs and CPUs share a common microprocessor design. A lot of you know the von Neumann design, and this has dominated the chip landscape for over 60 years or more. And as we saw with the GPU, it may not be the best approach for data-intensive and AI workloads like Gen AI. Let's look at why. So here you see a close-up, not of my company's chip, but of Intel Meteor Lake chip die. By most accounts, an amazing feat of human engineering. Let's focus on just the area at the top left of the chip. I have two arrows, one pointing at the L1 cache, which has the CPU instructions and data, and one pointing at the nearest compute core. So the core has to retrieve instructions and data from the cache, perform the operation, and store the results back to L1. All that data movement increases compute latency and power consumption. And like I said, right, maybe not a great fit for these data-intensive workloads like AI. So at GSI, we have introduced a new approach that addresses these challenges. That's a view of our chip at the top right. If we zoom in down to the SRAM level, you can see a fairly standard grid of SRAM cells. But right underneath in this chip, 24 of the SRAM cells, we have a bit processing core. And it lives on the same memory bit line as the SRAM. On average, each bit processor is 20 microns away from its associated SRAM group. And these bit processing cores are programmable by software. They can all run in parallel, and there are a lot of them. 2 million of these bit processors are interleaved throughout 48 megabits of that SRAM. The bit processors are connected to each, forming this powerful compute grid, to each other, forming this powerful compute grid that you see there at that inset. You can think of each of these bit processors as, they're pretty simple. It's a programmable Boolean engine that can mux in not only the neighboring SRAM cells, but also the neighboring bit processors in that grid. And although each bit processor is simple, the compute power and the energy efficiency lies in the bit processing grid that spans the entire chip. We have also, you'll see there at the bottom left, we've also interleaved an additional 96 megabits of SRAM local storage throughout the chip as well. So instead of like the L1 on the Intel, right, the L1 being over here and the bit processor here, we've also interleaved that external storage throughout the chip. Each bit processor has read-write access to its closest block of that local storage, which is SRAM, and on average, it's 100 microns away. So what I showed you was the first generation of our chip. We're also starting to work with a hyperscaler on chiplet designs for Gen AI and LLM. Here you see different versions of our IP for different edge, low power scenarios with budgets from 2.7 to 10 watts. Really for the edge use cases, under 5 watts is going to be what we're going to target. But here, what we're doing is, as the exercise, we're taking 6 megabytes of that local storage budget and then interleaving different numbers of bit processors through that. And we get pretty respectable tops for int8 and FP8. int8 seems to be the preferred quantized format for a lot of these language models. And then just briefly on token rates, this seems to be the preferred metric to measure large language models. Here you see 2 different plots. We're using Meta's Llama large language model, different parameter size versions of it. In both plots, the context window is a generous 34K tokens, 32K for the prompt and 2K for completion. And on the left, we can achieve a completion rate of just over 42 tokens per second, which is pretty good. And this is for that 2.7 watt design that you saw previously. And it's assuming, for that number, it's assuming an external DRAM speed of 800 gigabytes per second. But we've parameterized it in this graph because you don't always get that DRAM speed, depending on the technology you use. On the right, we've included also the prompt computation. The left was just completion. The right was prompt and completion rate. And it's a generous prompt size at 30K tokens, and we get a pretty respectable 30 tokens per second for that 2.7 watt design. And that's it for the review of my company's technology. This is Open Compute project, so this is not a slide to sell anything. In fact, we're offering for anyone that goes to this conference free access to one of our chips in our data center. First generation chip I showed you in the first few slides. Generation 2 is coming out early next year. It's going to have ×10 the local memory storage. And we just open sourced our compiler. So if you're interested in porting your algorithms to this new architecture, none of your x86 experience is going to be useful. It's a completely different way of thinking about programming a chip. But we just open source that. All right, thank you.
Thank you, Georgie. Great presentation. Actually, I'd like to propose that cost-effective computing infra for LLM AI service using AIM device, which is the SK Hynix first PIM silicon chip. So let me introduce SK Hynix's PIM product, AIM, which is GDDR6 memory-based PIM. Actually, from the beginning, AIM was created with a focus on just a GenV operation, which takes up around 92% of LLM processing time, as we discussed. And each AIM chip can provide 1 gigabyte of memory capacity and 0.5 terabyte per second of memory bandwidth when performing GenV operation. And I'd like to define some kind of key performance metric for LLM service. You can see that the right side, then performance per memory capacity is that teraflops per gigabyte. And in case of LLM response stays with a single batch, then it can be rewritten as memory bandwidth for memory capacity, terabyte per second per gigabyte. So if there is a kind of target per token processing time you have, then it can be expressed as the reciprocal of a critical metric. So as can be seen on the graph, AIM can provide 13 times higher performance capacity than GPU-A. So this means that AIM can process LLM inference in much shorter time than GPU. But perhaps even if you understand the benefit of AIM for LLM inference, you may be hesitant to deploy it, because you might think that you need to modify the existing CPU or GPU and also change the software structure on top of it. However, as we discussed, GenV operation takes up most of the LLM processing time, so that AIM can alone accelerate LLM service without any kind of accelerator like a GPU. So instead of replacing the memory in the existing accelerator with the AIM, we suggest making an AIM accelerator card and plugging it into your AI server. So we call this accelerator card as AIMX card. And in this case, there is no need to modify the existing CPU, GPU, or any kind of accelerator, and software modification can be minimized. However, for the AIMX card, it is necessary to develop an AIM control hub chip that connects the server and AIM through the PCI interface. Actually, we have already implemented the reference design of this AIM control hub chip in FPGA. So this slide shows that our AIMX architecture philosophy. So as shown in the right figure, the AIMX card consists of AIM control hub chip that receives jobs from the server and drives each AIM chips, and on AIM chips that stores model data and processes GenV function efficiently. So, and as you can see on the left, LLM consists of GenV function which occupies most of the processing time, and various other functions which occupies very small portions. So AIM chip focuses on processing fixed GenV function very efficiently, while the other various function can be performed by the AIM control hub chip. So in this way, AIMX card can kill two birds with one stone. So efficiency and flexibility. So it can accelerate various LLM models with high performance and low energy consumption. So here are the benefits of AIMX for LLM service. First, in terms of inference latency, 5 GPU-A systems processing time was around 7 seconds, but 25 AIMX card can provide 200 terabyte per second of memory bandwidth for GenV function and can answer in around 0.5 seconds. So 13 times shorter latency than the GPU. So if you have some real-time kind of a LLM AI application service, then it can be a good solution. Actually here, assuming that each AIMX card is equipped with just 16 AIM chips, so it can provide 16 gigabyte of memory capacity and 8 terabyte per second of memory bandwidth. But this is just an example, just a reference design. So 16 gigabyte per card is not the limitation. You can increase those kind of numbers to 64 or something like that. And in terms of energy consumption, first, the GPU is replaced with just a small AIM control hub chip, and GenV processed by a dedicated MAC unit inside the AIM, so reducing energy. Second, as GenV is performed inside AIM, so energy for off-chip data transmission is totally eliminated. Last, as the GenV performance increases, as I told you, the processing time is shortened, and the static energy is also reduced. That's why, in the end, GenV operation is possible with only around 17% energy consumption compared to the GPU. So you can reduce huge amount of operating cost as well. Actually, we developed the prototype of AIMX card introduced so far. So constructed the kind of AIMX reference system. As shown in the picture on the left, the AIMX prototype card is equipped with 2 AIM control hub FPGA chips and 16 AIM chips, providing 16 gigabyte of memory capacity per card. Currently, the 13 billion OPT model and Q&A application are ported to this system and now showcased at the SK Hynix booth now. Actually, we are a memory company, not the accelerator company. So instead of providing whole kind of this kind of accelerator card system, we are going to provide AIM chips and the reference design of this kind of AIM control chips and the accelerator cards, so that you can build your own accelerator card system optimized to your AI service infrastructure with our AIM chips. So if you are interested in building your own shorter latency and cost-effective LLM inference accelerator solution with AIM, then just let's have a collaboration together to build it. And please visit SK Hynix booth A8 and find out our PIM. AIM is no longer future technology, but can be deployed to your existing system right now. Thank you.
I think we have time for 2 questions. Anybody? It's a shy crowd today. Maybe? Okay. Well, oh, do we have one? Okay. Can you go to the mic so people can hear? There's a mic right there in the center.
So it was very impressive solution. Have you actually tried the real llama or something, and you're demoing that at your booth?
Yeah, actually, Llama is not kind of open source, so we are getting some kind of OPT 13 billion model. So we purchase those kinds of things to our system now. So and you can see that kind of a real demo. And then we have a kind of plan to put more heavy size model like a 40 billion model or something like that.
Okay.
Yeah.
And does your colleague, are you also presenting, you're demoing something?
Sorry. Oh, right there. No, we're not demoing anything at this conference. But you go to our website. We have some more demos and more benchmarks on large language models that we've been doing. Yeah.
Okay, thank you.
Thank you.
Awesome. Well, thank you. Thanks, George. Thanks, Euicheol.